Hi guys, so we are going to be continuing with our a new page of sketch notes in addition to continuing with our atom lesson. So before I move on to the main idea of this lesson, I'm going to just go over what fission and fusion are. These should be words that you have heard before but may not completely understand them. So take out your sketch notes. You can pause me right now so you can get your sketch notebook and make sure you have you can dedicate one page to fission and fusion, and then you're going to have another page for radioactive decay or half-life. They're the same thing. So while you're getting that, I'm going to hit the present button. All right, so fission and fusion. The first thing we'll talk about is fusion, because that's what this picture is over here. So fusion, if you think about the word fusion or fuse, that's when we're taking two things and we're combining them to make them into one. So for this, deuterium and tritium are two different versions of hydrogen. And what distinguish them, we can see that they both have one proton, but you can see that the neutrons are a different amount. So deuterium only has one neutron, where tritium has two neutrons, but usually hydrogen is found with 0 neutrons and just one proton. But if we have these two atoms and they are moving around at a super, super fast speed, kind of like in the sun, and they smash into each other, what happens is they actually combine and they become a new element because those two protons stay in the nucleus. So we can see up here, the two protons stay together, two of the neutrons stay together, and we end up getting our new element, helium. So we go from two hydrogens to one helium, and a neutron is released. And that release of the neutron and this smashing together to make a new element releases a ton of energy, and that's where we get our light and our heat from the sun. And then the opposite, so that's when they smash together. Fusion is the two atoms smashing together to make a new, bigger element. Fission is the opposite. So fission, you can kind of think of if you have a soda bottle and you open up the soda bottle, and you hear that fizzing sound. So what's happening in a soda is we have the caramel syrup and carbon dioxide, and when you open it, the carbon dioxide is released, so it's splitting apart. So fission of an atom is where we have one atom, and in this picture, we don't know exactly what atom it is we have because there's too many protons hidden, so we can't count all the protons to know what it is. But if a neutron, from here maybe, smashes into this bigger element, then we have some of the protons going into, let me just move my picture so you can see some protons moving into this atom and some protons moving into this atom. So when fission happens, we get two smaller elements. And again, a lot of energy is released. We have a few neutrons being released when that happens. So that's what fission and fusion is. All right, so we're going to move on now to half-life. So new page in your sketch notebooks. On the periodic table, most of the elements have at least one stable form. And we've been talking a little bit about stable forms, but there are also some elements that have unstable forms. And when they're unstable, what happens is they emit radiation when they break down. So they always want to become stable. So as they're decaying, they're emitting this radiation, and that's how they become stable. But they change. Something has to change about them to become stable. And that's what we call radioactive decay, or its element's half-life. So let's take 100 atom sample, for example. Let's say we have 100 atoms that are unstable and they are decaying and they're breaking down. So if we talk about the half-life of them, basically, if the half-life is 1,000 years, for example, every 1,000 years, that sample is divided by 2. So half of it breaks down to become a stable form. So if we have 100, for example, in 1,000 years, now these are just made up numbers, every element that's unstable has a different half-life. So I'm just trying to give you an example here. So if we have a 100 atom sample and the half-life is 1,000 years. In 1,000 years, we will end up, you just divide it by 2, and we end up with 50. So now we have 50 atoms that are unstable and 50 that have become stable. In another 1,000 years, we divide it by 2, and now we have 25. So far, we have whole numbers. This is nice and easy. After that, though, we divide by 2, and now we're going to start getting a decimal. So we have 12.5. And then another 1,000 years goes by, and we have 6.25. So thinking about these decimals and these numbers, divide by another 2, 3.125, divide by 2, 1.5625. Are we ever going to get to the point where we have 0? So I just want you to think about this in your head. Are we ever going to get to the point where we have absolutely 0 radioactive or unstable portions of that element left? So if the half-life, if you're dividing by 2, are we ever going to get to 0? And this is going to be part of your sketch notes. So I want you to think about that as you're going on and doing the simulation. Okay, so why is this relevant? So scientists use carbon dating or the radioactive decay to determine how old ancient specimen is. So this, for example, we have a picture of a dinosaur here. But dinosaurs aren't the only things. There were things around before dinosaurs. There were things after the dinosaurs, but all things that were alive way before humans even came about. So we know how long ago they were on the Earth because of how much carbon is left inside of them. And you should have learned last year in life science, doing the carbon cycle, that everything has carbon in it. So we get carbon inside of our body by eating something. So remember, glucose has 6 carbons, C6H12O6. So we have 6 carbons in every molecule of glucose that we eat. That's how we consume our carbon. The carbon that's going into our body, though, is an isotope of carbon. It's carbon-14, and that's unstable. Once we die, so anything dies. So we're talking about trees, plants, any organism. So people, bunny rabbits, whatever. When it dies, that carbon-14 is no longer replenished by eating new things. So it starts breaking down. So as soon as it starts breaking down and becomes stable to carbon-12, there is always going to be some carbon-14 left. And we just learned that by my example of 100 divided by 2 for every 1,000 years. Eventually, you're still always going to have some amount of carbon-14 compared to carbon-12. You're never going to hit that 0. So we can determine how old a specimen is when we find it based on how much carbon-14 there is compared to how much carbon-12 there is. Scientists know what the exact half-life is of carbon-14. I believe it's about 5,000 years, right around 5,000 years. So we can determine by doing sample tests on how much carbon-14 compared to how much carbon-12 there is, and we can tell exactly how old an organism was, or how long ago an organism was here on Earth. So what we're going to be doing today is just kind of doing a simulation that will show you how half-lives work. And you're going to find that simulation. As you do the simulation, you're going to continue adding to your sketch notes, but it will be posted on Google Classroom. It is already posted on our website. I don't want you to open it up from here because then I won't have access to the work that you've done, and I want to make sure that you get a grade for this. So you're going to open it up from the Google Classroom, but I don't have it posted yet because I'm not ready for you guys to start it. So when you open it up, the simulation is right up here. So I'm just going to go ahead and click that to open it. Before you do anything, though, you need to read through all of the directions of the simulation. So this is what it looks like. You have 2 paragraphs that you're going to read just for a little more background information about half-life. And again, add that to your sketch notebook. Our objective is to collect data. So while you are doing this simulation, you're going to have these questions in your mind while you're doing your sketch notes. So you should be answering these questions in your sketch notes while you're doing your simulation, or maybe you can answer it from the information I gave you before. So what is a half-life? What is radioactive decay? What's an isotope? And approximately what percentage of atoms decay in each half-life? And how do scientists use radioactive decay to date fossils and artifacts? So you really probably could answer all those questions in your sketch notebook right now. So you're going to follow along with the directions. The first step is to click on the video button, which is right here. You're going to watch this video, it's going to explain a little bit more about atoms and half-lives. And then over here, you're going to start the activity. So we have element A through element D. And you're going to, when you start, you have 100 radioactive of whatever the element is, so whatever of the sample. So element C, you have 100 dots here. I don't expect you to count them all. You have this little button over here that you can click on. Oh, maybe because we didn't start it, it won't let you click. So you need to have the years passed. So just trust me that it's 100 here, years passed. So every time you click on this, 1,000 years goes by. This color is a little bit hard to tell which ones have decayed and which ones haven't. So we can see that 50 have decayed in 1,000 years. We have another 1,000 years go by, and now we're at 25. Another 1,000 years go by. Now for this, it's giving you whole numbers because it's not going to have half of an atom decay. So it gives you the whole numbers. So eventually, in this simulation, eventually you will have 0. You're going to record your data down here. So just remember, in real life, you will never get to 0 when you have a half-life happening because you're dividing it by 2. So it's half of it is decaying. So you'll always have some left over. So you're going to complete this data table right here. And then when you're done with the data table, done with your simulation, what you are going to do is double click on this graph right here. And I do want you to add this to your sketch notes as well, but we will discuss it. I want you to think about what would a graph look like if we go from having 100%, so something just died of the carbon-14, for example. Let's talk about comparing the half-life for something that has once been alive. So we're doing carbon-14. So if we go from 100%, and every 5,000 years or so, half-life happens, what would your graph look like? So is it going to be a straight line from top to bottom? Is it going to be straight line bottom to top? Is it going to be curved? Is it going to be wavy? Is it going to be a horizontal line? Is it going to be a straight vertical line? What would a graph look like if we're graphing a half-life? All right, so you want to think time. Remember, time always goes on the bottom. It's always something over time when we're doing a timeline graph. So your time frame would be down here, and your percent, we're going to go by percentages. Your percent of the atom would be over here. So remember, we're starting with 100% and we are doing a half-life. So think about that and think about what your graph would look like. I will go over this with you to make sure that you have it correct, but I do want you to attempt it here. All right, so I hope you enjoy the simulation, and if you have any questions, let me know.